Welcome to another Great Cow Basic tutorial. Today we'll be looking at timer 0 using an interrupt and peeling that back to understand how it operates at the lower level. So this is focused on the logic green 8-bit LGT8XM chipset, and this is a tutorial. This is part of a larger set of tutorials. We're on number 10, and there'll be a handful more over the next few days focusing on different aspects of this chipset. So what does it look like? It comes in many different forms, but it's essentially built around the Logic Green technology as chipset, and it comes in an Uno format or many different formats. I'm going to be using a nano format, the green one on the top left. It looks like this, and in the past I've in the earlier tutorials we've added in some LEDs here at the bottom right there, and then we've added in a switch and ADC. Today we'll only be using the LEDs via the resistors that we fitted. And how are they fitted? They're fitted on a breadboard designed by Chris Roper in South Africa, and I can show you that what it actually looks like, so it's quite useful. So the layout is the same, apart from I move the potentiometer. I will turn the lab light on here, that might help. There we go, a bit more light on the job. So what I've done there, I've just moved the potentiometer to the bottom right. Chris has it on the, top left. Chris has it on the bottom middle there. For the eagle-eyed upon you who have been following these, you'll notice there's an additional wire in here today, and that is attached to an oscilloscope that we'll be using. And you will also notice that the LEDs are dimming. They're pulsing. Now here in the lab they're a lot clearer and a lot smoother than it looks on that camera there, but we're going to peel that back to see how this actually operates. Because today we're going to look at how we use timer 0 to make those LEDs flash, but they're actually simulating a square wave. So let's have a look at the principles of operations, and this is quite important that we understand this, is that we're going to generate a square wave coming out of onto those LEDs. And that square wave will have different pulses and different widths in terms of the distance here. That's called the different here, that will change, and that value changes and it enables us to control a motor. But we're going to look at that in some detail. I'm going to be using a couple of variables, and essentially what happens is if the LED variable speed is greater than what's called a pulse width module counter, then it will turn the LEDs on. If not, it would turn them off. It's an extremely simple program, but it's just worth recapping the logic. So if the LEDs in the main program, I'll show you that in a moment, is great, it just counts to 1 to 100, 0 to 100, and the PNW counter the same. And when one is greater than the other, the LEDs come on, otherwise they get turned off. And how does it work? The interrupt handler, which is called PNW handler, gets called every 256 clock cycles. So you can calculate how fast this happens. Now, what's important is I've had to slow down the processor to show you on the oscilloscope. So I'm going to try it initially at this slow speed, and then after we've had a look at the code, we're just going to take out the slow frequency, and we'll see a lot smoother operation. Now, what's important is this logic here in the code. Just spoke about this, and what we're going to do in our code in a moment. We're going to initialize the code at the top here, and then we have this a do loop, which essentially just sets the LED power 0 to 100, and then finally it sets it to in the other direction 100 to 0, and it just sets the power to what's the LED speed, and this is our test variable here. Well, every 256 clock cycles, this routine, our interrupt service routine, the PNW handler will be called. And if this variable that has been set is greater than our counter that we have set, it will set the LEDs on, as I've said, otherwise it will turn them off here and here. It will then increment our variable called PNW counter, and if it gets greater than 100, it just gets reset back to 0, so that it keeps going around in 100. So what we've got is a main loop, On the left here, the main loop on the left is continually operating, which is this segment here. And then the ISR on the right is called on the interrupt. Now, I just want to share with you, that's the program that we're going to be actually reviewing. But there is other magic happening inside of the compiler. There's this red stuff. And it's important to understand for all the interrupts, not just this timer, these things occur. So when you initialize a Great Cow Basic program, on the left, when you initialize it, it creates all the interrupt vectors for you and enables global interrupts. So you don't need to do those things. The moment you use the on interrupt command, it will do that for you. And then every time on the right there, every time an event occurs, it saves the context. Now that context is applicable to your program. Your program is different from another person's program. So the compiler will save the RAM registers that you're using. That could be changed by an interrupt service routine. And when it exits and completes, it will clear the specific event flag that was called, and then it will restore the context, leaving your program intact. That is the design intent of Great Cow Basic. We do three things. We initialize the interrupt, we save the context, and then we clear that event flag and restore that context as the third operation. Those are three things that happen in the background. You don't need to worry about them. They happen, but it's worthy of note that that event flag is cleared for you automatically. So let's have a look what's going on in the lab here. Well, we can see here the LEDs are getting brighter and dimmer. As I say, they're flashing slightly in the camera, but they are doing it because if I show you an oscilloscope, you can see that the square wave is working. We have a square wave. It should all go off as it is now in the oscilloscope, and the LEDs are off. And if you look now, the power is on, and the LEDs are on accordingly. So we have a program that operates. So how does it work? Well, here's the editor, the IDE, and I'm just going to rip through the standard pieces. We've seen all this before. We've set our chip up, we set a frequency, and this frequency is what I've said previously. It is running extremely slowly so that we can see it on the oscilloscope, because my oscilloscope doesn't operate at extremely high frequencies. We set up the LEDs and all the constants, and we've done that, let me think, 10 times before, so we can just move over those. Let's look at the next part of the program. This is the main part of the program, and I'll just zoom out slightly on there for us. This is the main part of the program, and essentially I define some variables. These variables I spoke about that we're going to be using, and then I'm going to initialize my LED control. And then I'm going to call that initialization routine, and in here we're going to initialize some variables to 0, and this is the important part that does the grunt work for us. On interrupt, timer 0 overflow, call our PMW handler, which is the interrupt service routine. This here does the three pieces of code we spoke about previously of initialization, setting up the cache of the context, and writing back that cache for you. Then we finally set up that timer. We set it to a postscript of 1 because we wanted it to happen every 250 cycles, and then we start that timer because it is not a free running clock, so we need to start that timer. Then in our do loop here, we count the LED speeds up to 100, then down from 100 to 0. So that is the main program that's going to run through and say whenever it gets to 100, it goes back to 0. So we want 0 to 100, 100 to 0, backwards and forwards. So how do the LEDs get controlled? They get controlled in our handler. It says here, the LED count speed, and remember this could be anything between 0 and 100. If it's greater than our variable PMW counter, then turn them on, else turn them off. And it just increments up this variable here. it says increase that variable by 1, and if it's equal to 100, reset it to a 0. So what you've got is two variables being compared, and that's how the LED works. The LED is being turned off and off, on and off at high speed. Let's have a look at what's happening over in the actual program here. So we can see it operating. If we go to the top of our source program, I'm just going to change the take the frequency here. I'm going to set that frequency to 32. You'll see that the oscilloscope may not work. Well, I don't know what's going to happen because I've not tested it. The oscilloscope, oh, it's actually doing something. I'm generally surprised. Now the LEDs down here are operating a lot smoother. And what we've done, we've generated a square wave to control the motor without pulse width modulation as a particular function of the chip. We've done this all in software. And we'll show you how you can do this in different methods with pulse width modulation later. But essentially, what we've built is an LED controller that enables us to simulate a square wave. It's shown us some other key pieces. It's shown you how to set up a timer, how to set up a interrupt service routine, and that there's a wrapper around that interrupt service routine generated by Great Cow Basics to support this chipset. These are important points to take away. Remember, I changed that frequency only to make it smoother for my oscilloscope. And as you can see, if you have a really good signal there, if I go out to the scope itself, let's have a look, see if I can actually increase the frequency on here. One moment. On my oscilloscope. And you can see I'm changing the settings on the oscilloscope. Oh, nice. There we go. That's running very nicely. So using interrupts with Great Cow Basic is a relatively simple program. Okay, so today I wanted to show you how to do that. I think I've achieved that using timer 0 with interrupt, and the things I've just discussed are applicable to all the interrupts available within the LGT8X chipset. Enjoy.